Welcome back to 345, and today we're going to talk about really the most important structural concept we've got, which is equilibrium. We design structures that we want to be static. The science of statics is the science of keeping things in one place, keeping them from moving, and we want generally all of our building elements to be in equilibrium. We'd rather not have them moving around or falling to the ground or tipping over. Equilibrium is a concept where we basically start by assuming the condition we want. We say that we don't want the building to move left or right, in or out, up or down. We don't want it to tip over. And then we use some of the vector geometry that we introduced in the last video to figure out how to do that. We look at what the external loads are that we're putting onto the building. We take the dead load of the building itself, and then we try to devise a load path, a system of elements that can carry all of those loads through internal forces down to usually a stable stratum of soil below in a way that allows the building to maintain its equilibrium. We'll talk about two types of equilibrium: translational, which means moving directionally through space, and rotational, which is exactly what it sounds, that the building isn't spinning around any of its axes. We ended the last video by looking at a free body, a point P. P could be anything, building, structural element, and we asked what happened when we put a load on it, an external load, in this case a 10-ton load. And we agreed that if there's no opposition to it, if there's nothing that's holding P in place, P is going to accelerate. Newton's law says that force equals mass times acceleration. So if you apply a force to a mass, and you don't have any opposing force, the body will accelerate. It will not be in equilibrium, and this is not a condition we want generally for our buildings. We talked also about the science of statics really being about finding ways to take all the loads that we're imposing on the building, translate them into forces, into vectors, and then to come up with vectors that can oppose those. So in this case, we have a 10-ton load being superimposed on P, and we found a way. Maybe it's through another external load, right? Maybe it's pushing back against P. Or maybe it's what we call a stress, an internal force that builds up that can resist P. And in this case, we have 10 tons pushing P down, we have 10 tons pushing P up, and P suddenly is in equilibrium. The forces balance out. There's no net force pushing it in any direction, and so there's no net acceleration. P is in equilibrium. If we translate this to kind of real-world situations, right? If we have a tug of war where one person is pulling on the rope, right, all of their weight, maybe 150 pounds or so of force on that rope, if there's nothing on the other end of that rope, right, the person's going to move. They're going to accelerate in the direction that they're pulling in. If we balance that precisely on the other side with another force that is 150 pounds, then the tug of war, the whole game, will be in equilibrium. It'll be balanced. Now, notice what's going on here. There are two external loads being put onto the rope, and the rope is developing a state of stress internally. And in this case, we call it tension. The rope is being pulled apart. So it's in equilibrium, but it's only in equilibrium because it's developed this internal stress, right, that's able to balance the two forces, the two loads being applied on either side. Now, we can also look at ways to balance, to put things in equilibrium by relying on this internal stress itself. We don't necessarily need someone pulling on the other end of the rope. If we affix the rope to something really, really heavy and really, really solid, concrete block wall, for example, we might find that we can pull on it with all of our might, 150, 200, 300 pounds, and the wall doesn't go anywhere, right? How does that work? Well, the simple answer is that a network of internal stresses builds up in the wall. And the one that maybe we're most interested in, or the one that's most obvious in this case, would be a resisting force that would be the friction of the wall on the ground. In other words, we can pull with 150 pounds, and the friction between the wall and the ground will develop up to probably well beyond that 150 pounds that we're pulling on it. So we don't have an active force resisting us. What we have is material properties, both within the wall and between the wall and the ground that are building up internal forces, what we call stresses, that allow the load that we're imparting on that wall to be channeled down to the ground. You could keep going, right? The ground also has internal stresses building up that allow the crust of the Earth to take that force and spread it throughout basically the entire planet. Now, stress is really important. We think about stress usually as kind of a bad word, right? No one likes to be under stress. But it's the mechanism by which structures can actually be made to work. In other words, stresses we can think of also as a capacity, right? An ability for a material and a structural element to resist those loads, to carry those loads. And we'll talk about the ways in which they do this. They only do it maybe 4 or 5 different ways, and we can take advantage of those to develop load paths throughout a structure. Now, when we turn these loads into forces, when we think about these mathematically, remember that we're going to use vector geometry. So every one of these 150-pound forces, we're going to draw as an arrow, and we usually draw these arrows to scale. So 150 pounds is 150 pounds is the same length arrow throughout the drawing. If we were doing a 300-pound load, we would double the size of the arrow. 75-pound load, we would have it. And then we think very carefully about the direction and the sense. So in this case, all of these arrows are actually going in the same direction, but some of them are positive, which we can say is maybe going to the right of the slide, and some of them are negative, right, going to the left of the slide. These are important because we can use those, the size of the arrow and the angle and the sensibility to actually do what's called vector algebra, to add these arrows up. We can do that mathematically, looking at how far in the x and y directions the arrows go and adding those up. Or we can even do it graphically. We can draw these in AutoCAD as what are called force polygons, and we can use the geometry of the arrows. We can simply maneuver them around to find out how they add up. And in this case, it's pretty trivial. All of these arrows end up equaling 0, right? They all cancel each other out. They all put the bodies that they're working on in equilibrium. If we want to think about some more kind of architectural examples of this, here are 2 where we have 1,000-pound loads that are being carried in 2 very different ways. So on the left, we have a sculpture that weighs 1,000 pounds, and we have a podium or a pedestal that is made of a material that's capable of building up enough internal stress to support that sculpture. And the way we draw this is with 2 opposing arrows. The gravity load of the statue is pulling down, right, toward the center of the earth, 1,000 pounds. And the capacity of the pedestal to hold it up is pushing up, right? It's a reaction. It's happening within the pedestal. And this is something that's a little bit difficult to visualize. But think of that second arrow really, again, as the capacity of a structural element, a material in a certain shape or enough of a material that it can build up this reaction to keep the statue in equilibrium. On the left, the pedestal is in what we call compression. It's being pushed together. All of the kind of particles of that podium are being smooshed. Right? That is a state we call compression, very typical among columns. On the right, we have an elevator cab with a couple in it who weigh 1,000 pounds, and the cable that's holding them up is also developing a reaction of 1,000 pounds. Again, that's a little bit difficult to see. We think of that reaction again as a capacity of that particular cable. And that's going to depend on how much of the cable there is, how much cross-sectional area it is. The bigger the cable, the more stress it can handle. It's also going to depend on the material. Steel will carry a very, very high load. Chocolate pudding will not, right? This is why we have structural steel and not structural pudding. Notice too that the arrows in this case, all the same magnitude, all really the same direction, straight up and down, but very different sensibilities. And again, just like in the tug of war examples, these arrows cancel each other out. And the sculpture and the couple in the cab are both in equilibrium, right? They are not moving, provided that the 1,000 pounds up and the 1,000 pounds down are equal and opposite. Where things get interesting is where the vectors don't quite line up or where they go in different directions. And here we can use, again, graphic methods or we can use some simple trigonometry to figure out what we call resultant forces. So here, for example, we've got a boat at a mooring, and we have two forces on it. Let's say that one is the wind, maybe, and one is the tide, or the flow of the river that it's in. And these are happening perpendicular to one another. One of them is pushing on the boat with a 600-pound force coming down, and we have ways of translating wind speeds or river speeds into actual forces, into loads that have magnitudes that we measure in pound. And the other one is pushing from left to right with a force or magnitude of 300 pounds, right? And our job maybe is to figure out what the total force on that mooring cable is going to be, and also maybe what the direction is, right? We might not want our boat to hit other boats or get in the way. Well, vector geometry allows us to take all of the forces that are acting on a free body, in this case the free body is the boat, and to add them up by taking the arrows and putting them head to tail, right? Basically telling a story. So in this case, we have the wind that's pushing with 600 pounds of force. We then take the tide, which is pushing with 300 pounds of force. We take the tail of one, put it next to the head of the other, and we have the wind plus the tide is going to give us a third vector, a resultant vector, in this case C, that, as you can see, will be the third leg of a triangle. And this is what we call our force polygon. In this case, it's fairly simple. It's a force triangle. And we can come in and we can use some fairly simple trigonometry. We can use sine, hypotenuse, and cosine. Remember, sine is the opposite leg. Sine of an angle is the opposite leg over the hypotenuse. The cosine is the adjacent leg over the hypotenuse. And the tangent of an angle is equal to the opposite side over the adjacent side, right? All good fun, right? Trigonometry is something that's worth brushing up on just a little bit here. We'll use it some to figure out some of these as we go forward. In this case, too, though, you can see that since we have vectors that are working at right angles, we could also come in and we could use the Pythagorean theorem to get the magnitude of that resultant vector of C. Whichever way we do it, here you see it solved. We could say that we want to find the angle first, and we could do that by taking the opposite of that angle, 135, dividing it by the adjacent, 270 kilograms, doing inverse tangent, and that'll give us a little more than 26 degrees. And we can then come in and we can use that 26 degrees to figure out the hypotenuse, to use one of the trigonometric functions to figure that out. Or we could come in and we could use the Pythagorean theorem, right? 135 squared plus 270 squared is going to equal C squared. Whichever way you do it, elementary geometry gives us a figure that you can see here that is the resultant. And notice that that resultant is larger than both of the forces that we're putting on it, right? Which makes sense. We're adding two forces together. And notice too that they both influence the direction of the resultant, right? The angle of the resultant. And in this case, because we have a greater vertical force, it's going to be a slightly steeper angle than we might expect. What we've done here is we've taken these two forces and we have figured out what they add up to. We can now come in and we could actually design that mooring line. We know what it has to be capable of resisting. We know that there has to be, for the boat to be in equilibrium, there has to be an equal and opposite arrow to this resultant. So 302 kilograms, but instead of going down and to the right, that arrow, the resultant within the mooring line is going to have to go up and to the left. And we can use that figure, the 302 kilograms, to figure out both what material that mooring line might need to be made of, and also how much of that material we might need. Now, we can apply that same principle to more complex situations. Here we have a free body with three different forces acting on it. And maybe this is a building that has both a gravity load and a wind load, and maybe we're also planning for a seismic load, right? There are three different forces coming maybe from three different directions. So long as we know the magnitude and the direction and the sense, we can do the same thing. We can take the heads and tails of the arrow and line them up, again, so they're telling a story, right? Heads to tail all the time. And we can come up with a kind of force polygon where we're looking at all three of those arrows lined up together, and all told, they will equal a resultant arrow that you see here. Now, notice a couple of things here, right? We have a very big negative component right here with the 10 pounds, and that is actually lessened by the fact that we have another vector down here, the 2.25 kilograms or 5 pounds. That vector has a little bit of a positive vertical component. So notice that that really takes out some of the verticality that this vector has. Vector geometry allows us to sum these up. It allows us to come up with a kind of resultant. And then remember, if we flip that resultant around, that's the structural engineer's job. That's what we have to find. We have to find a force that is this magnitude, this direction, but the opposite sense, so that we have an equal and opposite force working on that free body. And when we do that, what we'll find is that the force based on the resultant will keep the body in equilibrium against all of those three forces, right? You can see some of this at work if you look at cable structures in particular. Here, this is one of my favorite buildings because it's just a structures lesson kind of brought to life. This is the Pat Center in Princeton, New Jersey, which was done by Richard Rogers in the early 1980s. And Rogers basically designed a structure that was a whole set of free body diagrams and vectors. These lines are all what we call tension elements. They're like cables. They're actually steel rods, but they work like cables. They're resisting by going into tension, right? So we can think of them as being pulled from both ends. And you can see that they're attached to these steel discs. And here, for example, we have 1, 2, 3, 4 steel cables that are holding up the Pat Center's roof on this side. And the resultant of those 1, 2, 3, 4 cables is actually a line that is that direction and that sensibility, right, going down right to left. The internal stress that the big cable is providing to resist that is equal and opposite to the resultant. So it is being pulled up this way. And if you do the math, if you add up the forces in each of these 4 cables, put them head to toe, what you get is a resultant that looks exactly like this, right? That's at that angle. So here, Richard Rogers, great high-tech architect, Pritzker Prize winning architect, taking Structures 101 and using it to make architecture out of it, right? Not by any means the last example we'll see of that. So we want to now complicate things just a little bit so that we can talk some about structural elements like beams. When we talk about equilibrium, we're talking about 2 types. Translational equilibrium is what we've just been discussing, trying to keep a body in one position in space. We call it translational because we're trying to have it not translate, right? Move in the X, Y, or Z direction. We also, though, don't want our buildings to fall over, right? A building that tips over is going to be more or less in the same position in space, but it's going to be in a very different attitude, right? It's going to be flat on the ground instead of standing up. This is a problem of what we call rotational equilibrium. We not only don't want our buildings to move, we don't want our buildings to spin or to fall over. When the object spins in space, we call it rotational equilibrium. And this has to do not only with how much or what the magnitude of the forces are and what the directions that they come at the object are. It also has to do with where they occur on the structure itself. So if we have a little free body here, the pentagonal free body, if we put a 10 kilogram force on it at the top left, and we put a 10 kilogram force on it on the lower right, we'll be fine in terms of translational equilibrium, right? 10 from the left, equal and opposite, 10 from the right. According to what we've just discussed, that should be fine, right? It should stay in one place in space. But notice that because they have what we call a moment arm or a distance between them, those 2 forces are going to tend to make the pentagon spin. And we're going to have to come up with the curved arrow, a reaction that's actually resisting it, not in terms of left to right or up or down, but in terms of clockwise or anti-clockwise or counterclockwise, depending on where you're from. So this is a slightly more difficult problem. This is a problem not just of simple vector geometry, it's a problem of torque or leverage or moment. We have a lot of different words that we use in different situations. But this phenomenon shows up all over the place. If you're trying to unbolt a bolt, if you use a very short wrench, you're not putting a lot of torque onto it. It might be very difficult to loosen. If you use a very long wrench, you'll be putting a lot of torque, right? The same amount of force from your arm is getting deployed in a different place, right? With a longer lever or a longer what we call moment arm that's going to make it more effective. Building structures undergo the same phenomenon. And we have to think not only about how much force we're putting onto them, we also have to think about where that force is acting on the building. So to go back to this example, right? Some of you may have looked at our besuited guy pulling on a bookshelf and thought, or pulling on a wall and thought, yeah, okay, fine. I can see that he's pulling with 150 pounds. There's friction at the base that can build up 150 pounds of resistance or stress. But isn't he about to pull the wall over on himself? And the answer is absolutely right, that this is a problem not only of translational, but also rotational equilibrium. Note that he's pulling on the wall maybe 3 or 4 feet above where that resisting force, that friction, is occurring. And we say then that he's putting a moment that is equal to the 150 pounds, the force that he's pulling with, times that moment arm or times that lever arm. That is a number that we measure in foot-pounds or kilogram meters, and it is a measure of torque, right? It's a measure of how much rotational force is being put into the wall in this case. Now, what happens, just to give away the ending here, what happens is that the wall, hopefully, is so heavy that it imparts its own resisting moment, right? It has a very, very heavy weight, and it too has a moment arm, which is the distance between the kind of center of gravity and the point at which it wants to be a fulcrum, right, or an axle. So here, there's a point right here at the corner of the wall. There's the weight of the wall acting through its midpoint, and it will have a very, very short lever arm, but an awful lot of weight. And at least to a certain point, that resisting moment will mean that the wall not only stays in translational equilibrium, which we get from here, but it will also stay in rotational equilibrium, right? It won't fall over. Now, we have, as I said, ways of knowing exactly how much a material or a given structural element can build up stress within it. And these internal stresses are what we use to resist external loads. We can do this in a handful of ways. The two that we've looked at so far are compression. Materials have a resistance to compression. When we smush them, the particles start to bear on one another, and they have resistance to either changing dimensions or sliding past each other. If we do it exactly the opposite direction, if we pull the material apart, we say that that material goes into tension, right? It's a way that the material has to develop internal stresses that prevent those particles or those fibers, whatever's in there, from sliding past one another or from ripping apart. The two others that we'll talk about are shear, and this has to do with the material's resistance to basically planes of its sections sliding past one another, right? How again, the particles or fibers of the material can resist the tendency to slide past one another, in this case, across their main axis. And then finally, the really fun one is bending, and this is how beams work. And this is the capacity of a material to build up internal tension and compression stresses at the same time to resist loads that are, say, in the middle of a span. We can look up materials resistance to all of these in various tables, and we can use those basically to figure out how much of that material we need to resist the loads or forces that we're putting on it. And we do this through a handful, really, of structural types. Beams are elements that resist bending, right? This combination of tension and compression. Columns are simple elements that usually resist tension, but we also have what are called tension columns, where we're actually doing things like cables and things where we're resisting tension. Those are technically columns, but we call them tension columns. As we'll see, very few compression columns are that simple. We also have to usually design them as sort of miniature beams as well. We have two-dimensional elements, slabs and plates, that resist bending through this kind of internal stress, but along multiple axes, which makes them super efficient and also super interesting. And then finally, we have frames, and these are three-dimensional elements that can resist multiple kinds of loads. And usually these consist of beams and columns, usually in a rectilinear pattern, but very often with some diagonals to handle what we call lateral forces. All of these rely on material properties, resistance to these various types of force, and the shapes themselves, the shapes along their long axis and also across their long axis to resist these forces. When we are looking, for instance, at a beam, just to do a quick example here, we're trying to, again, keep everything in equilibrium. And beams are kind of unique examples of this because they deal with translational and rotational equilibrium so kind of apparently, right, or so obviously. And the way that I like to think about this, and I think the best way to illustrate the combination of the two, translational and rotational equilibrium, is to think first about a seesaw, right, a teeter-totter. A seesaw is basically a balanced lever. It has a fulcrum, it has the lever itself, and then it has loads that we're superimposing on it. And in the kind of simplest, dumbest seesaw, we have two loads that are exactly the same, and we have the fulcrum right smack in the middle, and we know intuitively that the seesaw is going to be balanced. Right? Now, knowing what we now know, we can say that there is also an internal stress in that fulcrum that has to be equal and opposite to all the loads we're putting on it. So we can add these two up. Right? Again, remember, we can put those arrows head to tail, and what we'll come up with is a single arrow, vertically oriented, with a sense of down, right, pointing down. 10 kilograms plus 10 kilograms will equal 20 kilograms. So the resisting vector, the resisting force, is going to have to be 20 kilograms pushing up. But this beam is in rotational equilibrium, right? These two are located 7.5 meters away, say, from that fulcrum, but they're equal and opposite, and they're both putting an equal amount of torque onto the beam. Intuitively, we know this balances. The way we can do this mathematically is we say that there's 10 kilograms times its lever arm, in this case 7.5 meters, so that is 750 kilogram meters, and it's going to be exactly the same on the opposite side. But notice what's happening. This load is imparting a moment that goes clockwise. This load is imparting a moment that goes counterclockwise, and that's really how they balance, right? It's not that they're just balanced in the vertical direction. It's also that they're balanced rotationally. One is going clockwise, one is going counterclockwise. These are what we call loads, right? Those are the loads that we're putting onto the seesaw. And this, the force in the fulcrum, is going to be what we call the reaction. Now, what happens if we change the loading, right? If we double the load on one side of the seesaw, we know intuitively that we have to change the shape of the seesaw. We have to move the fulcrum over closer to the heavier load. So if, say, we have a load of 20 kilograms and one of 10 kilograms, well, now we know that the reaction has to equal the sum of both of those. So 20 kilograms plus 10 kilograms, 30 kilograms. And now we also have to be very thoughtful about where we place all these things. And it turns out, if we kind of do the math, or if we just do this intuitively, that if we double the load on a seesaw, we have to halve the distance to the fulcrum, right? Now this has 20 kilograms times 5 meters. That's 100 kilogram meters of torque. And notice that on the left we have 10 kilograms times 10 meters. That too is 100 kilograms of torque. This 20 kilograms is trying to spin the seesaw clockwise. This 10 kilograms is trying to turn the seesaw or spin the seesaw counterclockwise. So again, we've added to the load on one side, but we've moved the fulcrum to keep the seesaw in rotational equilibrium. It's in translational equilibrium because 10 plus 20 equals 30. To know that it's in rotational equilibrium, we have to take both the load and its lever arm to see what kind of torque those two loads are putting onto it. Now, here's the kind of key thing that Leonardo da Vinci came up with and Aristotle came up with. A seesaw is really just a beam in disguise. And if we take that seesaw and flip it over, right, it doesn't know what the difference between a load and a reaction is. All it's feeling is the forces that are working on it. So if we flip that over, we get rid of the fulcrum, what we can say is that that same static condition is now a beam that we could use architecturally. A 15-meter span, supports on the left and right side. This now is going to be the load, 30 kilograms. And these now are going to be the reactions, 20 kilograms and 10 kilograms. And using the same math, we can see that the beam is in translational equilibrium, 20 plus 10 equals 30. And if we multiply each of those loads times its lever arm, 20 kilograms times 5 is 100, 10 kilograms times 10 is 100, we see that that beam is also in rotational equilibrium. So in a very short period of time, we've gone from thinking about what a vector is to taking an actual structural element and figuring out how it can stay in not only in one place, but how it can also stay in the same orientation, right? How we can prevent it from translating and from rotating. Okay, we will get a little bit less abstract. In the next lecture, we'll introduce some ideas about using the human body to think through cases of forces in equilibrium. We'll ask you to do some exercises at home in which we'll look for loading conditions and see if you can sense within your own musculature where you are feeling things like tension, compression, and bending.